So, hello guys. So I skipped a few topics. I hope that I skipped them, but you have not, right? So there are 4 lectures that I asked you to cover. 2 of them are vitally important, especially the mean value theorem. There is 1 lecture about optimization. I would say, practically speaking, delivering it in class helps very little because it takes much more time, much more effort to get a grasp of this topic. Of course, the fear I have is that many of you might not have, you see, I only have what, 11, 14 people probably, it's 11 truly, that are joining this platform. I do not know, even among the people that join, how much effort you put into this class. That requires, since it's mathematics, requires immense amount of effort. So what we do now, we start immediately with integration, and we continue with integration until we hopefully finish it, with enough explanation given. So in antiderivatives or integration, the first topic should be hopefully very easy to you, as we spend so much time on taking derivatives. Now imagine that what's happening is what happens rather often is that, let's say you wander into the lecture slightly late and you see the solution, right? So usually you think, here is a question, and here is this, you have to supply the solution. Now you have the solution supplied, you want to find the question. And I'm sorry, Batel, what do you don't ever bother. I'm very glad to hear from you. What do you want to ask, Batel?
Okay, so I have a question. I watched lecture number 17, and I thought we're gonna go over that with the global max, all of that. So we need to study that on our own, because for me it was clear.
Yes, if it's clear, then it's brilliant. There is no need to re-explain what's clear. But if people have questions, I'm happy to, after class or after the regular ordinary lecture, to go over it. It's just, I think that since the new developments, I was not counting, for example, on the final departmental final. I was not counting that this will happen. It never has happened, and apparently we fall under the umbrella. So that might mean that the final is very close. It might be right at the beginning of the finals week, right? Which means I have to hurry up and go ahead with at least integration to at least build you up on the basics. Which means as well that there is a huge risk. I'm not sure how much people are studying. My impression is that very, very inadequate amount. So I'm pretty worried. Yes.
Is it a certain? The test is not on Blackboard, right? It's a different application.
It's on my Open Math. It's you will soon receive another mail by Professor Suzuki, and you can actually find him on YouTube. If you type Jeff Suzuki, you can find his videos on YouTube as well. And he's directing it. Yeah, he's directing all the stuff on the final. So I'm pretty sure you know more about the final than I do, since I'm not quite in the loop just at the moment.
Okay? So I'm required to sign up. That's all.
Yes, you are. So it is departmental, definitely, right? So if you received the message, Zina, you never got an email, I will forward you the message.
Yeah, I also haven't received it.
Right, so you don't receive it through your usual email account, since Professor Suzuki does not have it. You have to check your Brooklyn College email. Not, I send email directly to the account you provided. You have to check. Good?
Okay, understood.
Good. Okay, so let's move on with this lecture again, guys, right? If you know the material, you have nothing to worry about. What you should worry about is how well you know the material. So here again, back to antiderivatives. Now you are supplied the answer, and your goal is to figure out what was the question. So suppose that you found out, here maybe you can ignore and not look at anything, you found out that the derivative is 2x. What do you guess was the original function? You might already see it on the screen, but maybe you have not looked into it. Do you know what's the original function?
It could be x squared followed by any other interval that's not going to be...
Right. So you might guess that the question was to differentiate x squared, or to differentiate x squared plus 5, correct? Because the derivative of a constant 5 here will disappear to 0. Or x squared minus 7. Or in general, you might expect that there was a question to differentiate x squared plus some constant. Okay? And here is a line. You try to guess. You see those functions, right, that I have over here? Let's see how good you are at guessing. So suppose that the answer to the derivative question was 7. What was the function? Right? So you have A, B, C, D, E, and F. Let's see how many of those you can figure out. Yes, wonderful, Sam. So the first part, you might guess that the answer will be maybe 7 times x plus any constant, plus let's say 7 or pi or any number, right? Minus 14, 7x minus 14 is a possible solution. So 7x plus a constant might be a good guess for here. Yes, Abdul, correct as well. Make sense? And you might see this immediately geometrically. F prime x equal to 7 means that when you think of derivatives, you imagine that you are measuring the slopes of the many tiny line segments that together connect to form the chain, which is the graph of the function. Now, if all of them have the same slope, that means that the little chains, the little line segments are all aligned, all aligned, which means that they are on the same line, and that line is it's a line with a slope 7. So the answer is 7x plus c. And then for b, it is x cubed plus c. Brilliant, Batel. All right. So this you might just guess, just because you are so comfortable with derivatives, or at least with some derivatives, you might guess this immediately. And what about c? The derivative is x squared. Can you figure what might have been the function? Exactly, Sam, right? So 1/3 x cubed plus c. And what about if the derivative is x to the power 5? What must have been the function? Wonderful, wonderful. Brilliant, right? 1/6 x to the 6 plus c. And then in general, what if I have x to the power of n? That's my derivative. What must have been the original function?
1 over n plus 1 times x to the n plus 1.
Brilliant. And then if the derivative is e to the x,
Plus c.
Yes, plus c. And if the derivative is e to the x, then the original function. Yeah.
That's e to the x plus c then.
Exactly, right? So wonderful, you got all of them. So how do we figure out here? Let's say for c, I just show you, or at least try to explain how I think of it. So I make many repeated guesses and I correct them, right? So first, I know that if by my familiarity with derivative, if I see a power 2, then the original function had a power plus 1, right? So if I see a power n, the original had a power n plus 1, because when I take the derivative, I subtract 1 from the power. So in a way, if you remember inverse functions, what I'm doing is I'm reversing the operation, right? So if I see that my answer is x to the n, I reverse the operation by imagining that you had an n plus 1 over here, yes? But then this n plus 1, when I take the derivative, it drops in front of the x, right? So there must be a number to greet it and cancel it to identically 1, right? So there must be a number in front here, and that number is 1 over n plus 1, because when I take the derivative, n plus 1 here will drop down. Does it make sense, guys? I'm assuming it makes very good sense. And notice that this formula is utterly meaningless only in the case where n equals to minus 1. So this formula works that the antiderivative of x to the n will be x to the n plus 1 as long as n is not minus 1. Okay? Wonderful. Here is another batch of values. And let's see how good you are at at guessing the antiderivative. So we have the derivative is e to the power of 5. What was the original function? One moment. Yeah, give me 1 second.
Sure.
Я включу камеру. Нет, не видно было, наверное. Может, бывает. All right, so go ahead, guys. What is the answer to A?
E to the 5 plus c.
Uh,
E to the 5x plus c.
That's right now, right? E to the 5,
Okay.
it's just a weird looking number, but nothing more. It's just a number. It's just 2.71 stuff, right? Raised to the power of 5. So it's going to be, it's the same slope. So it's e to the power of 5 times x plus c. Yeah?
So we should always write this. We should always put the plus c there, the constant.
Yes, why not, right? Because you're trying to guess, and we're going to talk about it more below, but you're trying to guess the function, and you're trying to not make a mistake. You're trying to make your guess as broad as possible. So then we have part B, right? So what about if my derivative, let's see if you remember, is equal to 1 divided by x? What is the function then?
If I recall, we had something that has to do with the logarithm.
Yes, that's brilliant, right? So, and Zina, you said ln x plus c, and that's a brilliant guess. There is only one thing that you should worry about, is that ln is defined only for x being positive.
Yes, you have to put ln bracket of x absolute value.
Exactly, right? You put absolute value around the x. You put absolute value around the x, and yes, you put absolute value around the x, and then the answer is ln of absolute value of x plus c. Wonderful. What about then the derivative of the function is x squared plus 5x plus e to the x? What do you think that one is?
I did this one already. It's the sum of derivatives, so it's going to be 1 over 3 x to the third plus 5 over 2 x squared plus e to the x.
And plus c.
And plus c, yes.
Brilliant, brilliant, right? So here again, guys, right? Here is how we work c, right? I realized that derivative of a sum is sum of derivatives, so I can work with each piece separately, right? So I can take the antiderivative of x squared, and roughly that would be 1/3 x cubed. I can take the antiderivative of this x, that would be 1/2 x squared. I know the derivatives, they commute with a constant, so I can move around. So just x, I need to find antiderivative for. And the antiderivative of e to the x is e to the x. And therefore, I have 1/3 x cubed plus 5 over 2 x squared plus e to the x. And I myself, I think, have not written plus c, but it's plus c. Now, let's see what others we recall, what other antiderivatives you might recall. Suppose the derivative came out to be cosine x. What is the original function? Sine x, beautiful. And in particular, it could be sine x plus 5 or plus 7. And David, you write capital X, which makes me feel you really want to study probability. So that sounds like a random variable. So E, the derivative now is sine x. What was the original function?
Isn't it just cosine x?
Well, that's a good guess, but derivative of cosine is minus sign. So you
Negative
make a
cosine
guess.
x.
Exactly, right? So that's what I do, and eventually you do it rapidly. I make a guess, and then I take the derivative and correct my guess, because the derivative might be almost what I want, but not exactly, right? Or I just, so I remember derivative of cosine is minus sign. So if I have derivative of minus cosine, that will get me an extra minus, yes?
Yeah.
So I hope, guys, I'm going fast through it, but it seems that you are kind of good at it, right? So here is how I am illustrating in my thought process, right? So I see that, well, if my derivative ends up being, my answer, my derivative is supposed to give me sine x, right? So then I begin. I take cosine, and I take the derivative, I get minus sine. So that means there must be an extra minus over here and an extra minus over here, because then I can take the derivative and everything is good. Make sense? So I kind of have this process. Take the derivative, my guess is almost correct. Then I go back to the formula and I see I need to modify it. I need to put a minus here, because this minus will be preserved, and minus times minus is plus. Good? So next is, what about secant squared? The derivative is secant squared. What's the original function?
Simply tangent x.
Exactly, right? Then just next, I see that you're versed at it. Let's wait a little. I'm sure that the others that are here will answer G. Derivative is secant tangent. What was the original function?
This one I don't know. I don't know. The one that you're like, because it's confusing, because at the same time okay, I'm not gonna say anything.
No, you can. Why not? I'm glad that you participate.
No, it's thank you, but it's fine. I don't want to be that one person.
What one person?
That guy that always just talks.
Well, I'm that guy that just always talks.
Well, you have the right
So
to.
you have at least two, and the others, guys, you are all hiding from me. It makes me feel lonely. Where is Zina? Yes, Alexa. So this is secant.
Why is it secant x? Why is it?
Because, well, you see, what happens is that you have to train.
I'm
and
trying
practice.
to give everyone a chance.
So when you take sorry,
it
Sarah.
took me 55 years to practice these examples. I said it took me really long to practice these examples to get the hang of it. But I think it's
You
that's
muted
it.
yourself.
But I'm saying I feel like you just have to practice, because they're very similar. The same questions.
Yes, well, when you
have to
practice differentiation, you eventually recognize the person or the function as a person by its signature.
There's a pattern, like exactly.
Okay, can you? I'm not understanding.
Yeah, I just noticed
this
the
one.
pattern sometimes.
Yes, so here is you see, you take the derivative of the 6 trigonometric functions. That gives you the first basis for guessing, right? So derivative of cosine is minus sine. So you know that when you have to go to reverse differentiation, when you start with sine, then you get something like minus cosine.
Yes.
Then you notice other derivatives. You see the derivative of tangent is secant squared, yes? That's how you could guess in reverse. You just recognize, oh, secant squared, it came from tangent. What comes from what if I see that it's a secant x tangent x, I ask myself what it comes from, and both Alexandra and Batel tell me it is secant, right? And that's correct. The derivative of secant, it just happens to be secant tangent. I would have not remembered it until I can derive those things. Always what you want to do is you want to have multiple ways of getting to the information. So you want to train, especially when it's under pressure. So for example, when I was taking exams, let's say when I myself took calculus exams, I would derive on the exam, on the goal, identities as I needed them, right? So it's like I started worrying, do I remember something correctly or not? I can derive it fast enough. If you can do that, then the material cannot be lost, because you can just always regenerate it. So the derivative of secant happens to be like the derivative of 1 over cosine, and I know that. I know I can use quotient rule and whatnot, or you now know chain rule, it's like cosine to the power of -1. So I know how I can do something, right? And I can get to the derivative, and that will be secant tangent as my final answer. Now the next one might be more challenging, so take your time and think about it. The derivative is cotangent squared. What can you do? So but there's a secant x times minus y. Right, you can try. You can. Yes, go ahead. Sorry, but what did you say?
I don't know. I was looking for derivatives on the internet, and I wrote a bunch of like list, and I just memorized it, but it might be wrong. They didn't have exactly for.
Well, don't try to remember many
times
things.
square.
See, much better is to just be able to remember. Say, oh, I remember derivative of sine is cosine. Derivative of cosine is minus sine. From there, everything else can be quickly established.
Isn't there something you taught us once that would be helpful for this type of situation, like for like when it comes to the identities?
Yes, so you want to know as much as you can. The more you know about those functions, the easier it is to figure things. Okay, so spend a little time. Let's wait, 5 minutes, and then I will reveal my answer.
Can I ask you a question?
Go ahead.
Give me a second. I just need to make sure this is true. Never mind.
In that case, I should ask you a question. It's a bit distracting, but how many of you, by any chance, are watching Babylon Berlin on Netflix?
No. I'm not. Sorry. I don't know what that is.
Okay.
What is it called?
Babylon Berlin.
Babylon Berlin? Does it have German subtitles? Does it have English subtitles?
Yeah, probably you can translate it. I think you can either put subtitles or dub it. Well, we want to go in the reverse, right? So we have here, and I didn't say, by the way, I didn't look at Batel's answer. It's just not like what I would have written, right? I can check if it's truly wrong or not. But derivative of cotangent is cotangent it's minus cosecant squared, right? Antiderivative of, yes, we're basically wanting to get in reverse. Suppose something had derivative equal to cotangent squared. Right? If it's equal to minus cosecant squared, I could have said it's cotangent, right? What happens if it's equal to
cotangent squared is equal to cosecant squared minus x minus 1 times x minus 1.
Brilliant. So maybe you can use that idea. So
how is that going to help me?
Well, think about it. So wait, Batel, I will reveal my answer, guys. And you see, there are many possible guesses. I'm not saying anything. Yes. Wait a little, guys, and get ready. Sure way to test it, guys. You're producing antiderivatives. If you are correct, you take the derivative of your answer, and that has to give you the derivative. Yes. So if Batel you say it's minus cosecant to the power of 4, then the derivative of that should be cotangent squared if you're correct. Okay. Every answer what you do, you can just take the derivative and make sure that you are correct.
I think I got the answer.
Okay. Let's wait a little longer and see what people would say.
You said it's better working backwards, yeah?
What I do is I make a guess and then quickly see if the guess is right or wrong, and I modify it. Right? If I am off by a constant, let's say the answer should have been x, but I get 5x, right? Then I just multiply by 1/5. I correct by multiplying by a constant.
Wait.
Okay, let's.
No, wait.
Okay.
20 seconds.
Sure.
Okay, I'm ready.
Good. So here we have we begin with our function, which is cotangent squared, and I think, oh, what is it? I try to think, what is it? It's cosine squared over sine x, right? And what can I do? What can I do? So then you recall this identity: cosine squared plus sine squared equal to 1. I hope you remember that identity. Yes. So so then I can see how I can produce cotangent here. I divide both sides of the equation by sine squared. Dividing this by sine squared will make the first part cotangent squared. Next part is plus 1, and the last part is cosecant squared. And therefore, I have that cotangent squared equal to cosecant squared minus 1. Yeah?
Say again.
Yeah, so so what happens is that we get the identity that cotangent squared plus 1 equals to cosecant squared. Right? And what's so special about cosecant squared? I just remember. I remember that the derivative of tangent is secant squared, and the derivative of cotangent is minus cosecant squared. So
Yeah.
cosecant squared is more familiar to me as a derivative than cotangent squared. You see, I think in reverse. Right? I can
Oh my God,
differentiate
that was
everything.
it.
Yes,
I was right
you
there.
you were there, exactly.
I
You see,
I started doing so much other bullshit after that. I'm sorry for my language. I started doing so much other stupid stuff after that. I got confused. I didn't know what I was doing.
no
I
trouble.
was too close.
It's really now when you took enough derivatives, you already recognize their so to speak their shoe prints. You know what the function used to be. So if I see cosine squared, I know that's the shoe print of what? What's the antiderivative of cosecant squared?
I can't hear you.
What's the antiderivative of cosecant squared?
Is it sine? Why am I blanking? Negative sign. Yeah, Batel said it.
Be careful, right? So you mean?
But I don't know if I'm right. I mean,
Yes. So with the symbol, I mean, it's what is it? It's inverse sign. No. Be careful, right? What you want, or maybe you mean 1 over minus sign. The antiderivative of cosecant squared is, first of all, it's if you take cotangent, take the derivative of cotangent, you get minus cosecant squared. Yes. Derivative of cotangent is minus cosecant squared. So what's the antiderivative of cosecant squared?
Is it negative
Exactly, right?
Negative cotangent?
Exactly. Right? You see that if I take the derivative of cotangent, I get negative cosecant. So I need to put another negative in front of it, right? So I have minus cotangent. And the antiderivative of minus 1 is simply minus x. So my answer is f of x equal to minus cotangent x minus x plus constant. Yes? Minus cotangent x minus x plus constant. It depends. When you say it's all about recognition, right? It's all about whether you, if it's somebody you're not familiar with, it's kind of hard to talk about. But if it's someone you knew for a while, you recognize this person instantly. Same thing goes for functions. So you're just not familiar with some of them, right? So what about problem I? If I have f prime equal to the cube root of x squared plus x square root of x, you have to guess what was the original function if that's the derivative of this function.
Wait, you want us to do I now?
Yeah.
Nah, fam. Fine.
Today's lecture is only about guessing, right? The guessing gets harder, but that's if you're good at guessing, you're good at half of the material that will come.
Okay, give me a second. How long are you giving us for this?
Well, I'll wait until I have an answer. Don't shout out. Just wait. I want to see if how many people answer. To H, I will go back to H, but I'll just let's
No,
just
answer H.
Oh, I did. The answer to H is minus cotangent minus x plus c. Yes, you understand. I translate this cotangent squared to something else. I write it as well. I write it as cosecant squared minus 1, and the antiderivative of cosecant squared is minus cotangent.
Is I has something to do with the length?
Well, I don't know.
This, can I ask a question?
Yeah.
I'm sorry. Do we use n+1 in this scenario?
Well, it's I don't know. See, your questions are like if I step on something, is it going to be a mine? I want you to know where the mines are. Imagine I'm not there. All right, you figure out. If you believe in your reasoning, if there is reasoning behind it, at least there is something to guide you.
Your cats.
Exactly. That's precisely what you hear.
That is the answer to the question.
That's spring.
I think I got the answer.
All right. So wait a few more moments. I want to see that others have it. Yesterday actually was at his things. It was by the computer. It almost interrupted the lecture.
The cat?
Yeah. No, he does it on purpose when he wants to. It's basically it's bilking. No, not attention. He demands. What do you call it? Ransom. He doesn't want my attention. He doesn't care for me, but he just wants ransom.
What do you mean?
Food.
Oh.
Or to be let into some place. If some place is locked, he might demand to have it open. He's a smart cat, by the way. That's a good question, by the way, regarding the number of cats. I told you, remember about the philosopher in a dark room. It's how many you imagine. Well, give me a moment, guys. You think about this question. I will move one moment. I'll be right back.
Guys, what do you think the answer is? I know I'm the only one here that's not on mute.
I'm not sure. I tried to separate the thing into a fraction for the exponent.
Yeah. Abdul, I got 5 over 3x. Do I have to do the reciprocal because of the derivative?
All right, guys, I'm back.
All
so
right.
Yes.
Can
So
I say
so I have Abdul and I always mispronounce his name. How do you say Yixuan? Zang, right?
Yeah.
Yixuan?
No.
No, of course not, right?
Yeah, you're right.
Yeah. So the idea, yes, I see two of you got the same answer. When you have consensus, that usually is a good sign.
So I got opposite from them. I got 5 over 3x, but I'm not sure now. Is it 5 over 3x plus 5 over 2x plus c?
Yeah. So here is first we want to.
Wait, hold on. I can't see. Okay.
Okay. So here, where is it? I don't know. I lost my marker for some reason. Some sort of bug. Well, hopefully you can see what I'm pointing at, right? So you see this x to the power of 2/3. That's I mean I convert basically the powers into a number, and the second I convert to a number, it ends up being 2/3 here and 3/2 there. And then when I anti-differentiate, I have to add 1. Right, so it's 2/3 plus 1, which gives me 5/3. And then there is nothing in front of this x, so I have to have the reciprocal of this number to grid it, right? So 5/3, when they come down, they have to be multiplied by a number that will cancel 5/3 to 1. So that would be 3/5 here. And similarly, for the other part, we have 5/2. We have 5/2, right?
Yes.
Yes, so 5/2 will then require 2/5 to cancel. Yeah. Here is that was I. Now here is another problem. Let's see. Can you solve this one now? The derivative is 3 times t to the 4 minus t cubed plus 6t squared divided by t to the 4th, and your goal is to find an antiderivative. Retrieve the original function.
I'm sorry, what's the question, Professor?
Oh, you see it over here. You have to find the original function. You see right at the end of my screen at the bottom here.
How long are you giving us?
Oh, we can wait.
Professor,
Yes.
I feel so dumb, but can you recommend some questions like this that we can solve? And I know you said in the book, but I don't really open the book much.
So why not? It's very heavy. Good workout.
No, I mean there's so many questions there. I'm like.
So I mean, you just do the odd ones. You don't have to do all of them, but the odd ones have solutions at the back. So you do the odd ones.
I do them. I do some of them.
Yeah, and some says there are some questions in open math. Truly, for calculus, it's very easy to find questions. They just say antiderivatives or a list of solved antiderivatives online, and you will find it. It's just way too much.
Okay.
Right?
Thank you.
Yes, Magnus. This lecture not on my site. I post it on YouTube. Yes, so it's every lecture since I think the last 2 or 3. I started posting them on YouTube, on my YouTube channel. If you want to, I will email the link. And guys, so you know this topic is covered on my ordinary lectures that I recorded some time ago. All right, so just I have this calculus lecture sequence, so it's there as well. Not quite this lecture note, but you know, something essentially the same. Abdul, you made that's what you got so far. What's next is the easiest. It's the easiest thing to do next. Think about. Oh, David, be careful. You see, guys, one thing that you should not do is invent solutions. You have to be sure that how do you know if you're correct? You don't just close your eyes and make a step. It's not a class in religion. You have to, whatever you say has to be justified by reasoning, which is at least by calculation, right? You can check your work by taking the derivative. David, do you believe in your solution?
Yes.
Well, then you are a person of conviction, and your conviction is wrong. Why is it wrong? First of all, you reverse anti-differentiation, yes? And think about it. What are the simple rules, right? Derivative of addition is a simple rule. Derivative of constant multiplied by a function is a simple rule. But this looks like you have a quotient. If you have a quotient, you might imagine that there might have been, in that sense, some quotient rule involved, if that's what you think. And the quotient rule is definitely not simple. Quotient rule is not derivative of numerator divided by derivative of the denominator, which is what you reversed, right? You said, aha, I see a function on the top, and I see, a second, yes, I
If
see.
it's 0 over 0, isn't it that you could take the derivative of the top and the derivative of the bottom? Isn't that L'Hopital's rule?
L'Hopital's rule is about calculating limits. And again, there is a lecture on L'Hopital. Make sure that you understand why it works. L'Hopital is a way to solve limits. We're not asking limit as, let's say, a numerator goes to 0 and denominator goes to 0. Right? We don't take derivative of numerator divided by derivative of denominator. When you understand, there is a very, what is L'Hopital rule? It's just a recognition that you have a limit that looks like the definition of the derivative, nothing more. Watch the lecture. It's about solving limits. Many of the limits involve, within them, they involve like a deformed derivative. Right? But that's not, don't memorize processes. Otherwise, just it makes no sense. Quotient rule is not simple.
Right.
And you see, you would be correct if you know, quotient rule were the derivative of numerator divided by derivative of denominator, but that's not the case.
Right.
Yes?
No,
Okay.
it is not. Right, okay.
Good. So are we ready? So let's solve this. So the very first thing you might have thought to do is you don't like division, because division involves quotient rule, and quotient rule is kind of hard to think about. So I distribute the t to the 4 across. I distribute across, and then I see that the derivative is really 3 minus 1 over t plus 6 over t squared. And these are pieces that I know how to anti-differentiate, because you see, each of those pieces I can figure out. So what is this? This is 3 minus 1 over t plus 6 times t to the minus 2. The antiderivative of 3 is 3t. The antiderivative of 1 over t is ln absolute value of t. So it's 3t minus ln absolute value of t. The antiderivative of t to the power of minus 2 is minus t to the minus 1. So that's my answer. Make sense? I reduced it to addition of pieces, and I know how to anti-differentiate each piece. And I use the idea that derivative of sum is sum of derivatives. Okay? And what David wrote is a very common mistake that I'm sure many of you will make, because you try to just guess simply. You think, okay, I know the antiderivative of the numerator, and I know the antiderivative of the denominator. Why not mix them together? The antiderivative of the denominator is 1 over 5 times t to the 5th, and the antiderivative of the numerator is it's 3 to the power of 5. 3 over 5 t to the power t to the 5 minus 1/4 t to the 4th plus 2 times t to the cubed. But you see, the problem is that numerator and denominator do not yield a simple derivative. I hope that that is clear. Here are some more functions. Find antiderivatives for a. So a is 5x squared plus 2 to the x plus 1 over x. Let's see if you can do that one. So solve A, B, C, and D as quickly as you can, and we will look through them. I might have forgot to mail you my Zoom link today, right? So I guess you remembered how to get to me. How are we doing, guys?
To answer without even writing it.
Do I know the answer?
No, can I try to give you the answer without even like? Can I do it without? I didn't write anything. I tried doing it without writing. Can I?
All right, just a second, guys. So are you ready? The rest of you, are you ready?
Yeah, I'm ready.
Yeah.
Alrighty, okay, Joel, go ahead. I guess give the answer.
So what I did was I separated each of them. I got for 5x squared, it would be 1 over 3x to the third.
Mm-hmm.
And then for 2x, I got for 2 squared, I got 2 squared. And no, 2 squared.
It's 2 to the x.
No, 2 to the x. My bad. 2 to the x times 2 to the x ln of 2, or 1 over ln of 2.
So which one?
2 to the x 1 over ln of 2.
Okay.
And then the last one is simply ln of x, but x is going to be absolute value.
Brilliant. So the full answer for A is just 5 over 3x cubed plus 2 to the x divided by ln of 2 plus ln absolute value of x. Yes? The reason that works is as follows, right? You deal with each piece separately. X squared as antiderivative 1 over 3x cubed. 2 to the x. Well, think about it. When you take derivative of 2 to the x, what do you get? You get 2 to the x times ln of 2. So you need to grid this ln of 2 that will come away from it by writing 1 over ln of 2. That's the antiderivative, right? If I take the derivative of this expression, you see what I do? I take 2 to the x. I take the derivative. I see that in addition to 2 to the x, when I take the derivative, ln of 2 comes out. So I need to multiply by a constant. And that constant will be 1 over ln of 2. Now the derivative is identically 2 to the x. And here I just know that the antiderivative of 1 over x is ln absolute value of x. Good? So that was solution for A. Now go ahead and then solve B. If the derivative is 1 over 1 plus x squared, what is my function?
I see what you did. Professor, can I ask a question?
Go ahead.
In regards to trig, isn't 1 over 1 plus x squared equal to cotangent? No. What am I saying?
Right. So there must be, first of all.
But am I on the right tracks here? Like, am I on the right track, or
for what? For how to find the derivative, right? So I think I get what you are saying. You didn't say it. So you ask yourself which functions produce a derivative of the form 1 over 1 plus x squared. You do know one such function, and then you are, I suppose, on the right track. And I now understand what you meant. It's not that it's equal. You're asking me, is the antiderivative of 1 over 1 plus x squared? That's why I didn't understand right away. And yes, so what is that?
isn't 1 over tangent x?
No, not 1 over tangent.
Bro, I'm confused.
What happened, guys? I hear one person, and the rest of you, are you alive? Do I need to call ambulance? Yeah, that's a question. I think I'm not, but so what's the answer? Derivative is 1 over 1 plus x squared. What's the answer?
Hey, give me a sec. Okay, so let's think of it this way.
All right. So I guess I will reveal it.
I gave you my shot.
Let's see, guys. So first, b, right? The derivative. Do you remember we took derivative of inverse trigs? So Abdul, good idea, right? You're almost there, right? Derivative of inverse trigs. So make sure that you understand that tangent minus 1x does not mean 1 over tangent. We went over that, right? It's not 1 over tangent in no way. What is this?
Okay.
This means the function that if you put tangent inverse, if you put this expression into tangent, it will cancel the tangent, right? That's what the minus 1 means. Remove one instance of tangent.
Inverse.
So it's a language, right? It's like the minus 1. It's like it's gonna cancel the outer layer of a tangent if it's placed on top of it, right?
I understand.
Right. So that's the notation. So derivative of tangent inverse, as we explained, is 1 over 1 plus x squared. Make sure you can derive those identities, right? I would have been forgetting them again and again and again. Right? I don't have a particularly great memory. So it's 1 over 1 plus x squared.
Whatever.
Right? Only because I remember it. Only because I recognize. What you do is, first thing you train is to recognize the footprints of functions you are familiar with, right? And then if you recognize, then tell me what's the derivative that gives you 1 over root of 1 minus x squared. What is c? What does this look like?
That looks like sine.
Brilliant. So it is what? Sine inverse.
Sine inverse x plus c, if you want to put it that way.
Good. That's very good. Okay, guys. So what you do is, whenever you forget, right? Whenever you forget the identity, derive it. Eventually, it will become second nature if you do that this way.
And the last one is very simple, also. Based on that,
yes,
it's going to be secant.
Precisely, right? So this now involves nothing more than recognition, right? So derivative of sine inverse would give you this expression. Derivative of secant inverse will give you that expression. Okay. So here now let's talk a little bit about this movie. Have you seen the movie Usual Suspects? I'm sure you have, right? You're American afterwards. You must have seen this movie, right? Nope.
No.
Well, you're not what? Right. No. Where have you come to this country, guys? Right? Usual Suspects. It's with Kevin Spacey. It's a pretty good movie. Kaiser Sosa, right? So here is the question that I'm going to ask, right? And try to think about it. Let's see if you can solve it. That's really an interesting question, right? So you have to round all the possible suspects, right? So it's going to be very important. You might not think, because you're not doing anything specifically, with mathematics, but it ends up in physics, or you have to be sure that you get the right function. You have to catch the right culprit. So imagine that the problem was that the derivative of some unknown function is 2x. You are very good at guessing now. So what was the function you were saying? The most inclusive collection of functions. You need to get all the usual suspects. All right. So what would that be? X squared plus c, you say, right? Right. You have seen functions of the form x squared plus 5, or x squared plus 7, or x squared minus pi. The derivative of all of them is 2x. So that's a family of functions. For different values of c, it's a different function. So you know that this satisfies the solution. But is Kaiser Sosa among those suspects, the culprit? Right? What if, for instance, I told you that here, something that you don't understand at all, I wrote it in symbols, this expression, its derivative will be also 2 to the x, okay? Is it something entirely new? It looks definitely not like x squared. Is it entirely new? How can you be sure, right, that you gathered every suspect, every possible function whose derivative is 2 times x? Maybe there are functions that are more exotic that you have not seen, and their derivative is 2 to the x. You understand what I'm asking? You have to be sure that you catch the criminal, the right culprit. So you want to make sure that you captured every possible function that satisfies this situation. Okay. So you might wonder, is g of x truly one of them in disguise? Is it truly maybe some x squared plus some number, right? And here, let me try to illustrate my point a little better, right? So again, we are back to this problem. F prime x is equal to 1 over 1 plus x squared. Give me an antiderivative for this function. One of them.
Derivative for that function would definitely be -1. Would it be negative 1 over 1 plus x squared?
So the function, the derivative is 1 over 1 plus x squared. We want an antiderivative for it. What is that?
Oh.
Yeah, just be careful.
Okay, fine. Can we just write inverse tangent x?
Yeah. So one possibility is inverse tangent x. Yes.
Plus c.
Yeah. Well, but in other words, you really is one family is functions that essentially look like tangent inverse. Plus c means the graph of tangent inverse moved up or down. They look exactly alike. Geometrically, they have the same shape. It's just like moving the function, the graph either up or down. Now, here is another possibility. What about the derivative of cotangent inverse? If you try, the derivative of cotangent inverse will be -1 over 1 plus x squared. Yes?
Yeah.
And so I might get another guess, right? I might guess minus cotangent inverse of x. Do you understand what I'm saying, right? So is my guess somehow very different in its species from tangent inverse? You see, I have another guess is minus cotangent inverse, and this one is tangent inverse x. Are they very different? You agree? The derivative of cotangent inverse is minus 1 over x, 1 minus 1 over 1 plus x squared. So if I place an extra negative and take the derivative, that will be again 1 over 1 plus x squared. So minus cotangent inverse of x and tangent inverse of x are both antiderivatives of the same function.
Can you explain this one more time? Like, what's the point you're trying? I'm not getting your point.
My point, you have to figure out antiderivatives in their totality. You understand? You have to, you imagine that your goal was to figure out the function that produced this antiderivative, the specific function that produced this antiderivative, right? You must be sure that you're not making a mistake. You might have said, well, the best I can do is it's tangent inverse plus 5 or minus 7. Essentially, your answer is the essential part of your answer is tangent inverse, correct?
Okay.
Maybe there are other functions that satisfy and they give you the same derivative, right? So that you have not included an entirely different function.
Right.
That
Like
also
we
has
just
the
said,
same.
negative cotangent, inverse cotangent is the same thing as negative 1 over 1 plus x squared. So you could just throw another negative in front of there, is what you're saying.
So what I'm saying is at least visually, negative cotangent inverse of x, it's not visually the same as tangent inverse of x. So we can try checking for values. Let's say if they are the same, right? Some people say maybe they are the same. So Zina says they would both be the same. Let's try to see. Well, what is for example tangent inverse of let's say, well, of what value? Let's say of 1/2. Or let's try simpler. What's tangent inverse of 1? Tangent inverse of 1. Simpler thing. What's tangent inverse of 1? In other words, which angle is mapped to the ratio 1 by tangent inverse? So the answer for my question was this, right? You know that if my angle is 45 degrees or pi over 4, then opposite and adjacent are of the same length. So if my angle is pi over 4, tangent of pi over 4 is 1. So tangent inverse of 1 is pi over 4, yes? Now, cotangent inverse of 1 is pi over 4, but there is a minus. So the answer here is minus pi over 4, whereas the answer here is pi over 4. So they are not the same function, for sure. What's the difference between those two functions? You understand what I'm saying, right? Imagine that I wanted you, I mean, you see, you might say geometrically speaking, x squared plus any constant, it's the same graph, right? Because it's the same parabola. Let's say x squared or x squared plus 1 is just a shift of the parabola 1 unit upwards, right? So it's only really a change of coordinates that make them different. Geometrically, there is only, it's the only solution you suggested when you anti-differentiated to x is x squared. In other words, the only solution you suggested is just one parabola. Could there be other shapes, more exotic graphs, more exotic functions that will also produce derivative equal to 2 to the x? That's what I'm asking. Guys, do you understand what I'm saying when I mention geometrically, right? So you might think that x squared and x squared plus 5 and x squared minus 7 are different functions. And you're absolutely correct. They are different functions, but their graphs look exactly alike. The graphs look like motions, like rigid transformations, rigid shifts of the same geometric curve, right? So y equals x squared is this parabola. Y equals x squared plus 1 is this parabola lifted upwards. Y equals x squared minus 4 is this parabola moved down 4 units. So you get the same shape, right? In essence, the family of those functions are closely related. I'm asking what happens if I get two functions that look somewhat differently cosmetically, minus cotangent inverse x and tangent inverse x. I'm hoping cosmetically they don't look alike, but they have the same derivative, which means what? And by cosmetically, I mean only in the way I named them, right? What can you say about their graphs? What do you think?
They have similar slopes at certain points.
Can you hear me, guys? So I noticed somebody was unable to hear me now, right? Can you hear me now?
I can hear you.
All right. Okay, good. So, yes. So the derivative is the same. So what's the relationship between minus, yes, Sarah, try to come back. So minus cotangent inverse x and tangent inverse x, how do you think are they related? Their graphs, first of all. What do you think about their graphs? Can you see it?
Are they exact opposite?
But okay, so you're supposing they're exact opposite. So that means that you believe that more exotic versions of antiderivative, say of 2x, are possible. So x squared is just one version of antiderivative. You believe there might be many more exotic versions. Am I correct?
I guess.
Okay, let's think of it. So exact opposite is very vague. What do you mean by exact opposite?
Not sure how to explain. Let me think about it.
Okay. Melissa, you have been quiet. I was wondering what you think about it. Reflections of one another. Well, reflection, even that is a bit vague. Well, are in the same as functions. They are not the same functions, in right? Maybe I misled you with my my saying that it's saying not the same. They are not the same functions, right? You see, Zina, that if I plug, say, 1 into tangent inverse, I get pi over 4. But if I plug 1 into minus cotangent inverse, I get minus pi over 4. So
Okay,
as
hear you
functions,
now.
they don't generate the same numbers. Yeah, great, Sarah. They don't generate the same numbers. Okay, interesting. So let's try to see what's the relationship between cotangent inverse and tangent inverse. What do we say? Right. So let's take a look at it. And here is that relationship. Suppose that I draw first just tangent inverse of x. Yeah, tangent inverse of x. If I draw it inside of a right triangle, then that means that if I apply tangent to this angle, I get x, which means I'm having a right triangle with opposite side, say x, and adjacent side 1. Make sure you understand me, guys. Now, this angle here I drew in blue is actually cotangent inverse of x, because what do I know that? Because if I apply what trigonometric function should I apply here so that the ratio of, let's say, adjacent to opposite will be x. Right here I have opposite over adjacent. Here I can think of adjacent over opposite, and I know cotangent gives me adjacent over opposite. Yes, so this angle is actually cotangent inverse of x. Do you follow me, guys? Do you follow me, Melissa? That's why I picked on you, right? You see, I just think logically. I think logically, and I think, okay, this is cotangent inverse and this is tangent inverse. Good. And tell me now, what can you say about those two angles? What can you say about the relationship between cotangent inverse and tangent inverse? I put them on a right triangle. What can I say now? No. We already saw by, no, they're not equal, no. Clearly, they're not equal. Look at it. I can create different values of x, and I can have, they are, well, they are angles, so you have to be careful when you say distance. So you don't, when you apply tangent or secant or whatnot, you're creating ratios, right? So and when you apply inverses, then you're going back to angles. Exactly, David. They add up to pi over 2. I just don't like your adherence to degrees, but you are absolutely right otherwise. They add up to pi over 2. You see? This angle plus this angle plus this angle has to be pi, or in particular this plus that, since this is a right angle, has to be pi over 2. So that's what I wrote over here. Tangent inverse of x plus cotangent inverse of x equals to pi over 2. I don't have to do any calculations to know that in general tangent inverse x does not equal to cotangent inverse x, because, well, what can I do? I can create all sorts of triangles. I can make this angle very wide or very narrow, and this angle then will be very different, right? If, for example, I push this side very high up, then this angle is closer and closer to 90 degrees, whereas this angle gets smaller and smaller. So they are, in general, not equal. But the sum always equals to pi over 2. You follow? So look what that means. That means that if I rearrange, if I solve for cotangent, if I move cotangent inverse across, if I take cotangent inverse across and I take pi over 2 here, I realize that minus cotangent inverse x equals to tangent inverse x minus pi over 2. So this function is actually tangent inverse x plus a constant. It does belong in the same family. Do you understand? Take a moment, make sure that you understand what I just said. Okay, let's move on. Here is another problem. Suppose I have the functions cosine squared x and minus sine squared x. Are those functions the same, guys? Are they equal? Is f equal to g as functions? In other words, do they always agree on inputs? Or?
Not really.
Not really. They actually very rarely agree on inputs. You don't need to even plug anything to realize this number is, in general, either 0 or positive. So in general, it's positive number. This number is either 0 or negative. So they rarely ever agree. As functions, they are clearly different functions, correct? But let's take their derivatives. I take the derivative of the function f. It would be by chain rule 2 cosine x. Derivative of cosine is minus sine x. The derivative is minus 2 sine x cosine x. And then I take the derivative of g. And I also get minus 2 sine x cosine x. Okay? And here is our question. So f and x and gx have the same derivative. How are they related? Are they related? Wonderful. Careful, better, right? Melissa says that if I square, I mean, Melissa, you wrote it slightly incorrectly, but but I get your point, right? The square of the first plus the square of the other equals to 1, and that we can see from this right triangle, right? We remember Pythagorean theorem. cosine squared plus sine squared will give us 1. Which means what? Which means that minus sine squared x equals to cosine squared minus 1. So that means that the second function is just the first function minus 1. The difference between them is a constant. Okay? So here is, in general, a question that I try to ask you. Okay? Suppose I find that the derivatives of two functions, like in this case cosine squared and minus sine squared, I find that the derivatives are the same. What can you say about the relationship between these two functions? Do you understand my question? As you know, Freud would have possibly said here, Freud possibly would have said, diese zwei haben eine verbogene Beziehung. In der Öffentlichkeit halten sie sich voneinander in Abstand. Or I thought it's very funny, but I guess you would not laugh. So I wrote you the translation. These two have a hidden relationship. They keep their distance from each other in public. Do you understand?
Sounds like me and my ex-girlfriend.
That was so funny.
Yeah, I know. I'm a very funny guy. I wanted to leave it in German, but then I figured, too hard for you. So do you understand what I'm asking you now? Right? Do you understand how to solve this? So the derivative of the function f and of the function g are the same. They are the same. So what can you say about f and g? What's their relationship?
So then if you were to put them into an equation, if you would put them, if you put f of x and g of x, how do I put this? Let's say this, for example. Can I try to ask? This is just asking: is f prime of x plus g prime of x equal to? Let's say f prime of x plus g prime of x equals to some arbitrary number.
Well, almost. The answer is.
Then would that mean that f of x and g of x equal the same thing? Or equal the same derivative of no.
More importantly, I want your reasoning for it, right? So first of all,
okay. No, continue.
So they have same slope. Yes, I want your reasoning. They have same slope, guys. It's kind of very, very evident, right, what happens here. And I already told you the answer, or at least in Freud's language, I told you the answer. What is the relationship between f and g? What do you think? So Melissa says they must either add up to a constant. Well, if I have, let's say, derivative is 2x. So I have x squared and x squared plus 1. X squared plus x squared plus 1 equals to 2x squared plus 1. They do not add up to a constant necessarily, right? So when you add, you are not quite following what I just wrote here. What's happening? Guys, derivatives. What's the most important part about derivatives? Do you remember? Das heißt streicheln. You pet the curve. Derivatives tell you how to pet the curve. No? What does it mean for two functions to have the same derivative? If you turned your screen, you could have shown me by your hands what it means.
They're parallel to each other.
That's brilliant. They are parallel to each other.
And that's why you said that relationship, but they can never. They have to keep distance in public.
Yeah, so they have a definite relationship. But look at it. derivatives
They
here.
cannot
Look at
touch
it.
each other.
Slopes are the same, right? Well, maybe if it's the same function, then they do, right?
Mhm.
So you see this? Because
Yeah.
what is the derivative really telling you? When I think
The
of
slope.
derivative, I imagine really it's a description of the orientation of many tiny line segments, right? So there are microscopic line segments that build up the chain that makes the graph of f, and another line segment chain that will build g. And those line segments for each x are the same. So we have the same slopes, which means that we are tracing geometrically the same curve. Do you understand? Geometrically speaking, there is only one antiderivative because you know it tells you how to move your finger to trace the curve. But doesn't matter if you trace the curve at the lower part of the screen or at the upper part of the screen. It doesn't matter if you do this or if you do this here, right? You are still getting the same. So Melissa, it's not necessarily that we're seeing the same curve from different sides. This is slightly different. This means that I'm looking at two curves that have the same tangent. For every x, you have the same tangent. It's like one astronaut on the x-axis is observing one curve and then observes another curve. And notices that anywhere he stands on the x-axis, the tiny line segment above him for f and the tiny line segment above him for g are oriented in the same exact way. Does it make sense? And wonderful. Isn't it? It's simple, guys. You understand? There's nothing to understand here. It's just a very much what you call it touchy-feely, right? So what do you do? Here is the argument, one argument possibly, right? To make it very simple. So it's always nice to if g and f are essentially the same, then g minus f will be 0. So I let k of x equal to gx minus fx, right? And then I take the derivative. Oh, I don't know what g minus f is, but I take the derivative. The derivative of a difference is difference of derivatives. Yeah, it's g prime minus f prime, which because they have the same derivative, this number is 0, right? So now I have a function whose derivative is 0, which means what? That's very easy to visualize. It means that all the line segments that built up the curve are aligned and are horizontal. So if I'm an astronaut on the x-axis, I see the aligning curves. You know, they are building what? What are they building? The derivative is 0. What are they building? What are they building? If the derivative of the curve, a horizontal line, a straight horizontal line, brilliant. You see that derivative is 0 means, let's say one tile is 0, the next tile is 0. Just imagine when you do derivatives, you are just in a very fancy, highfalutin way explaining the orientation of many microscopic tiles, in this case line segments that are attached to each other to form a curve. So that means that the function k is a constant, which means that g minus f is a constant, which means g equals to f plus some constant, okay? What does it mean in particular, guys? In particular, this means the following, right? Here is, suppose that, let's see if you understand this, okay? Suppose that you see this problem, right? And you are guessing that the solution is x squared. Derivative of x squared is 2x, yes? Now, an alien comes on this planet. Let's say he understands your notation. He's able to read it, but gives you the solution. Gx equals to whatever this thing is. So he says you put it here, this function, you differentiate, you get 2x. What is this function? What is this thing? Write to me, what is your best guess? What is this function that the alien placed here? You understand? You can take the derivative of x squared and you get 2x. Now the alien gives you this suggestion. This is the function that the alien likes to differentiate on.
We can't see it. Scroll down a little bit.
Here. You see, you have this expression here, yes? Yeah? What's the derivative? What's the derivative?
Why can't it just be
Well, derivative of that function, Melissa, you're saying is 2x, correct? Am I reading you correctly? You're saying derivative of this g function by the alien is going to be 2x. That's known, right? That's what we are told. I'm asking you what is g of x. So you're translating. You're trying to understand what the alien is. Well, be careful. You say n derivative of, let's say, 5 times x squared is 10x, not 2x. Sam, so be careful with what you write. Maybe
is it x squared plus c?
That's precisely right. It is x squared plus c. So whatever the alien placed here, that's
Because it doesn't matter what constant is there. And
well, it might matter, but the point is that the function that the alien brought could not have been extremely exotic. Do you understand that? It was not super exotic. So whatever they do on this planet, they just have different notations or different formulas. This function will look like what? What if you were to plot this alien function? What would you see? What shape do you see? It's not necessarily the same function. We don't know it's x squared, but what do we know based on what I just said? And Batel, do you realize if two functions have the same derivative, what are they? They are parallel. Yes. Because you see what I'm saying, because what does it mean for the derivative to agree for each x? For each x, the tiny line segments have the same slope. For each segment, they have the same slope. For each segment, they have the same slope. So the curves are parallel. So from the geometric point of view, there is only one function like this, because there is only one curve. You can imagine drawing with those many tiny lines, you trace the curve, because just you see, from the point of view of calculus, every curve is just a bunch of microscopic line segments attached together. It's like a chain. So if you attach them with particular orientation, you're going to always generate the same shape. That's intuitively clear, correct?
Yes.
So, but from a function point of view, you can have this chain, move it up or move it down, right? Or move it even to the sides. But in this case, the differences will be the same chain, either up or down.
Professor, I have to leave.
All right.
Have a great night.
Have a good night. Right. So g of x, derivative of g of x is 2x, means that g of x is x squared plus c. I do not know what c is. I might figure it out. That's going to be very important, guys. Super important for what will come. Yeah, so even though they might look different, their curves are parallel.
Thank you, Professor. I'm going to have to go. I just wanted to say that I appreciated the lecture.
Oh, thank you. Take care, Sarah.
Thank you. Bye.
Bye. So, okay, Hannah, take care. Make sure that you keep on top of everything. All right, guys, if you have to go, you have to go. I'll just finish this quickly. I'm not going to continue much beyond this point. I want you to know two things. The mathematical tool that makes it rigorous is the mean value theorem. I want you to definitely understand mean value theorem. But intuitively, you might have already known that, right? Because, well, derivative equal means that, well, for whatever functions I have, whatever the x, I have the same line segments have the same slope. The way the line segments can have the same slope, if it's the same line segment or if it's parallel line segments. And any curve is viewed from the lens of calculus as a bunch of parallel lines, many small parallel lines. So here is one parallel line, then the next parallel line is like this, the next is something else. And definitely if the derivative is 2x, that just means that that the lines go like this. First, at x equal to 0, the line is segment is parallel to the x-axis, horizontal. Then when the x is slightly more, then it becomes positive. It's like this, right? So when I understand the derivative is 2x, I imagine here is a line segment. Then the next line segment is a little bit positive. The next line segment a little bit more positive. Next line segment a little bit more positive. And I trace the parabola. If I go back, the line segment has negative slope. I go back, it has negative slope. I go back, it has a negative slope. So I traced parabola out of lots of tiny line segments, like even smaller. That would be a very good, accurate representation of the parabola. Does it make sense? So geometrically, there is only one curve. But mathematically, this is the family of functions. Fx plus c is the most general solution. So if you can guess one solution, you essentially know all the others. They're not going to be very complicated. They're going to be essentially the same. Good? Do you have any other questions? Well, in that case, all right.
All right, thank you, Professor.
No trouble.
Thank you, Professor. I'll print it. I'll try to solve it, and I will come back with a bunch of questions. I know.
Sounds good. Batel, you're doing well. You sound a little sad.
I'm nervous. I don't know how to get
Oh, what?
better in class.
No, you're getting better.
I never had such a problem like this with math. It used to be so easy for me.
Well, math. If math is easy, that means it's easy math or too easy math. Math is never easy. It's never easy to me.
Yes.
Yeah. Well, the next exam I will post it. I can even post it now. Essentially, if you cover the 4 lectures, you have the background to do the second exam.
So we need to cover the lectures up to this.
Yes, 4 lectures altogether, I think, right? What I skipped because I moved to integration. Okay, so I'm going to post the next exam essentially very soon. I can do it now, I think. I want people to cover the material.
And you don't have a review, like short videos like you had for the first exam, correct?
No. When I first made it, again, I noticed people are not really watching calculus, so I did not make more.
Thank you for the videos. They help.
And don't be worried, relax.
Yeah, they're very good. Thank you, Professor.
No, they're all right. I mean, but don't be worried. It's okay. Do your best. You are some of you, those that work. I can see improvement, right? Even if the improvement is not extremely fast, you're not thinking about it in the right way. The school is, it's just like a game. It's like you go to a Luna Park and you haven't won the teddy bear. I mean, you can buy a teddy bear. It's just really not significant. It's far less significant than you imagine. If you understand something, that's something to be really proud of. But don't worry about the grades. I never have. Okay. Do your best in understanding material and what? Sorry again.
I'll see you in the fall.
Well, yes. If again, we all fall. I fell. That's exactly. We will all see each other in the fall. As the Germans say, wenn einer für uns fallen soll, der andere steht für zwei. When one of us should fall, the other stands for 2.
No, I'm not gonna fail. I'll see you in the fall. In the fall semester.
Oh. All right, guys. So have a good one.
You too.
Good night, Melissa. Good night, Batel. Good night, Yihuan. I'm hoping I'm not butchering your name again, right? Good night, all. Chag Sameach. בארץ, מה עושים בארץ עדיין?
חג עצמאות. מדינת ישראל.
אבל יש עוצר. הם לא ייתנו לאנשים לצאת.
בסדר, עושים בבית. טוב, בסדר.
All right. Take care, guys. Have a good one. Good night.